We're only covering 2 sections. I'm going to get through this one probably today, and then we'll spend a couple days on the final section in this. We have a few definitions to start us off. I'm talking about discrete random variables. We know what discrete means. Talked about that at the very beginning. Do you remember? Not continuous. It's the opposite of continuous. So it's like countable. We can list out the values. So if we're talking about random variables, we're talking about a numerical measure from a probability experiment. So we have to have a value to it and a probability of that value. If it's discrete, it has to be countable, a set number, so it can't go on to infinity. Continuous has an infinite number of points. We are focusing on just the discrete. For example, discrete might be flip a coin 10 times. And count the number of heads. Okay, I know I am only going to flip it 10 times. Okay, and then I'm going to stop. Can you give me an example of a continuous variable? I mean, it can. It can be time. So, I could say the length of play practice.
Yes.
Okay, all we really know is it's going to be a positive number. It's going to be bigger than 0. Can we have a practice with a time of true 0? No, you at least have to walk in for them to tell you to go home, right? But could I have decimal values in there?
Yes.
Absolutely. Is there a definite stopping point? Do we know it's going to be cut off by the 3-hour mark? No. So there's a true infinite number of variables there. So for each of these, I want to decide if it's discrete or continuous, and then what kind of values can we get out?
Golf is dismissed at this time. Golf is dismissed.
The number of light bulbs that burn out in a room of 10 light bulbs in the next year. Good. That's discrete. We can count them. Okay, what kind of values would it have to be? 1 through 10? Could I have 0 light bulbs that burn us? Okay, so it would be 0, 1, 2, 3, all the way up to 10. I know it can't be more than 10 because there are only 10 light bulbs in that room. All right, B, the number of leaves on a randomly selected oak tree. Discrete. We can count them. Probably don't want to, but we can. What kind of values could we get?
1, 2.
Could I have 0 leaves on my tree?
Yes.
1, 2. Is there a stopping point?
No.
No, it just keeps going because there's an infinite, or no definite, like an oak tree can only have 500 leaves on it. It will never have more. There isn't a rule like that. C, the length of time between calls to 911. Continuous. Okay, what kind of values could we get for that? Would you say, Gianna? You got distracted. Focus. Okay, there's no maximum amount of time. Could we have a negative time?
No.
Could we truly have absolutely 0? There has to be some kind of pause, right, for us to like hang up the phone and pick it up again. So just anything greater than 0. Okay, because it's continuous, I can't list them out. We can have decimals, we could have infinite number of places. So that's showing us the difference between discrete versus continuous. Today we're focusing on just the discrete ones, and we're looking at the probability distribution. So we just got done the whole chapter with probability. When we're looking at the probability distribution, it's just a table, and it lists all of our possible outcomes of x, and then the probability. of each. So we'll list our x values, and that's why it has to be discrete, because if it were continuous, it can't list every possible x, and the probability of each one occurring. So let's look at an example. Suppose a basketball player is asked to shoot 3 free throws. Create a possible probability distribution for x equals 0, 1, 2, or 3 shots made. Okay, a possible probability distribution. So I didn't give you the actual probabilities. What are my x's? Okay, think about the things we already know about probability. It has to be between 0 and 1, and all of them have to add up to 1. Okay, give me some probabilities. What do you think is probability of shooting 0? 25%. Okay, what about 1? 15%. 2? Gotta have a 67, don't we? Have to. Have to.
Did you see Mr. Lee's shirt today?
No, I didn't.
Oh, I 60 would make it a
I need to
lot.
see this.
Wait, no, that's too big. That's too big.
Okay.
1776 is when I put the.
Yeah.
It's a waste of
That's funny. Oh, we can't do that one.
Yeah, this is a good talking point. Why does that not work?
It's too much.
It's too much. Okay.
So do
40?
yes.
Okay, so then what would this one have to be? 0.2, 0.20. And I know, quick check, every number is between 0 and 1. Does it add up to 1? Okay, so that's a sample probability distribution. Not that hard. Okay. So take a second on your own, look at each of these and decide yes or no. Are those probability distributions? Okay. Doesn't add up to 1, so that's a no. What about this one? Negative. Okay, what about this one? Yes, everything is between 0 and 1, it adds up to 1. So we know how to verify if something is a true probability distribution. All right. Let's draw a graph of the probability distribution and describe the shape. We haven't done that in a while. Do you remember describing our shapes of our graphs? What were our options?
Bell.
Yes. Skewed left or right or bell-shaped. And that's why we need the graph, just to visualize that. All right, we're not going to do anything too fancy here. We're just going to put our x, and these would be our probabilities. So my possible x values. I'm going to go ahead and just put 0 here so we can see it. It's kind of hard to read it on the axis. And that's pretty standard when you're listing those possible x's. They don't have to just start at 1. All right, so our probabilities. Looking at our numbers, we have some pretty tiny ones all the way up to 0.58, so I might count by 0.1. And we're just going to do our best here. All right. So 0 has a probability of 0.06. So a lot of times you'll see these probability distributions with just a dot and a vertical line going up to that. So 0.6, where's my line? 0.58, so that's just under 0.6. Two has a probability of 0.22. 3 has a probability of 0.1. 4 is 0.03, and 5 is very tiny, 0.01. So how would you describe it? And how do we know that? Yeah, we look, here's the peak and it's extending off to the right. So the tail extends longer that direction. All right. Any questions so far? So the two big things that we need to talk about with our probability distributions are finding the mean and standard deviation. So that's where we're going next. Just like most things that we've done, there's a formula for finding it, and you have your handy dandy formula sheet, right? So, this will be very helpful to have. We can also use calculators for this, so I'll show you both options. The actual formula. So we know from before, mu stands for mean. What's the symbol mean? We're going to add them all up. X times P of X. So it's actually a pretty simple combination. If I look at this, find the mean of the probability distribution, which represents the number of prime movie rentals in a week. So I have my distribution. Basically, if I were going to do the mean by hand, I just need to add one more column for X times P of X, the X times the probability. So 0 times 0.06, 1 times 0.58, 2 times 0.22, 3 times 0.1, 4 times 0.03, and 5 times 0.01. We pause there. All right, and then what do I do with those? Add them all up. What do we get? Okay, so it's saying on average, people rent 1.49 movies a week. What if I asked other questions from this probability distribution? What if I said, what is the probability one movie is rented? Uh-oh, my board just froze. Actually, it died. Okay. So what would be the probability of one movie being rented? Well, it's actually easier than that. I already told you. Here's one. The probability of one, 0.58. 58% of the time, people are renting one movie. It's easy to overthink them when we start doing more. What if I said the probability of more than 3? That means it could be more than 3 means it could be 4 or 5, so you would get 4% or 0.04 either way. All right, so I could ask you other questions about these distributions. Is that one okay? All right, so does that mean if I took a sample of people? So Brian is telling me on average people are renting 1.49 movies. Does that mean if I asked each one of you how many movies you rented, you would all answer something that when we averaged it would be 1.49? No, why not?
That's just the estimate.
Okay. Is every sample going to match the whole population? No, and we've talked about that a lot, that I can pick different samples and get a different number every time. What do you think would happen if my sample got larger? What if I asked everyone in the school? Do you think it would be closer to 1.49? What if I asked everybody in Monroe City? It's going to be closer. So we know that the larger our sample gets, the closer to the true mean we should get. I put one on here. And now my touch screen isn't working either. I'm going to have to restart my whole computer now. Oh, that's fun. Yeah. My technology doesn't always like me. No, it's when my slate dies, then like it messes up everything, so I have to restart.
I was beginning to think it when I was in here.
It might be, actually. That's the last time I had trouble. You're bad luck. Okay, so if I just gave you a sample, could you find the mean? If I gave you a sample of 100? We've done that before, right? How would you find the mean? Add them up, divide by the total.
I'll do it.
No, I'm not doing that.
This is the same thing, what we're getting from that probability distribution. I want you to recognize the connection there. When we have that probability distribution, it's telling me, okay, I had 0 show up, and it's saying from the set of data, what's the probability that a 0 happens? Are you okay?
There's so many flies flying around, man. Trying to kill them.
You scare me, I thought.
I thought there was something
There's
coming
like
at
one
me.
just sitting by me and Abram.
Would you like a fly swatter?
Yes.
Yeah, so there's something.
Yeah, built in flash.
You have one, don't you?
I do,
I
I
thought
do.
something was gonna fly at me.
Thank you, Miss. You're welcome. See you later. So if I found the number of zeros and their probability, and then found the number of ones and their probability, the twos and their probability. The probability is a decimal, right? And if I take it times the probability, that's the same as adding up all the individual ones. So that's this mean. It seems a little arbitrary when I'm saying take x times p of x, but it comes from the same set of data. Okay, 2 equivalent ways of doing it. You would get, if we do this one, you guys didn't want to, but we are going to get 1.49, the same as our last example. Oh, good for you. Did you get 1.49?
100 numbers is too many.
Oh, hey, it unfroze.
Maybe she was actually.
She might be bad luck, I don't know. And like we already said, as the number of trials increases, should get closer and closer to our mean. What we expect long term is the mean, the expected value. So if I say find the expected value, that's the same thing as finding your mean. And I'm looking at that. All right, so let's look at this one. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. The probability the female will survive the year is 0.99791. Compute the expected value of this policy to the insurance company. Expected value means what? The mean. Okay. If I want to get my mean, I need my x times p of x. So x is the value to the insurance company. So if somebody buys their policy and lives the whole year, the insurance company doesn't pay anything, they pocket that $530. What is the probability that that person will survive the whole year? Okay, but what happens if the person does not survive the year? Okay, the insurance company pays out,
So would that be negative?
it would be a negative because it's a loss, but they didn't truly lose $250,000.
Because
You
there's
lost.
249,000.
Yeah.
407.
Because of what.
Because they already pocketed the $530.
Why would
That
that
the
go
person
on the
paid.
right?
It's not the probability. This is the value to the insurance
So
company.
you
So,
subtract 250,000 from
mhm,
So
because they
to
already
get
got paid from the person,
the,
and
to
then
get
they
the
have.
probability they will lose,
You subtract.
you subtract
Yes.
one minus.
So 00209.
So that probability is 1 minus. So if I
couldn't
ask
be
you,
an insurance person because I would definitely lose the $249,000. I don't know, they must just be lucky.
well, no, they have, it's called an actuary. They do a lot of stats to determine based on your risk factors. This is how much we would expect to pay out. So as long as we're insuring 500,000 people and we want to get this much profit, how much should every person pay?
My dad's
I
not
just-
the reason they have to pay them.
No, I'm just saying, like, if I owned an insurance company, we would definitely go bankrupt because everyone would all file a claim the same year and then.
You guys seen the movie
Doom and gloom.
Have you guys seen the movie G-Force with like the hamster?
Okay, so how would I find my mean then?
Yeah.
Add. Multiply.
Multiply. You would have to get your x times p of x. add those together, and we get their expected value of $7.50. So that's their expected profit. Now, will that work if they only insure 20 people? No, because if one of those 20 people doesn't survive the year, the insurance company's in a lot of trouble. But if they insure 200,000 people, would this work? Yes. So that's why this has to work for large numbers, wouldn't work for a small number.
Does that mean like that? How much they pay monthly?
This is just how much money the insurance company would expect to make in a year. So if I insure 100,000 people, I'm expecting to make $7.50 profit on
Per
every
person?
person I insure.
Per person? Okay, I was about to say, I don't know.
Yeah, it would be
Make
for
money
every
at all if they,
Okay. Standard deviation is a little bit uglier, but actually still not that complicated.
Sure.
I'm sure.
That's complicated.
It has a square root. What's this symbol tell me? Add up x squared times p of x minus, what's this? The mean squared. Okay, so we could do this by hand. I'll show you how to do it by hand, then I'll show you how to do it on your calculator. Okay,
Thank you.
so you're welcome. If I went back to, let's go to, that one with my random line through it. Okay. If I were going to have to do the standard deviation by hand, you would need another column for x squared p of x, which really just means I need to take this number or times x, right?
Oh, yeah.
I have to take x p of x times another x to get x squared. So 0 times 0 is still 0. 1 times 0.58 is 0.58. 2 times 0.44. 3 times 0.3. 4 times 0.12. 5 times 0.05. Okay. Then, my standard deviation formula says the square root of the sum of our x squared p of x's, so I'm adding up that column, so I get 3.09 minus our mean, which was 1.49 squared. So if I plug that in,
We put it in parentheses under the square root.
as long as your square root carries over the whole thing, you're fine. And I get
33.27.
that's our standard deviation. Alright, let's see how to do it on our calculator.
Stat.
But we have to know how to do it by
Stat
hand.
one. Stat.
Alright, so first, we are going to enter this in our calculator. We are going to put the x in list 1 and the probability in list 2. So remember, don't delete out our lists. It does matter that they are in the same order because you have to keep the probability with the number. Does everybody have that? So now we're going to calculate one variable statistics, but we are changing something. Our list is L1, frequency list is our probability, so that needs to be L2. So if you hit second number 2, that puts it in L2. And then enter. And X bar, that was our mean. Didn't we get 1.49? Standard deviation, you notice they don't give you a sample, it's just population, 0.9627. Same thing we just got. Okay, so you can do it all on the calculator. You just have to, in your one variable statistics, your frequency has to be L2, your probabilities.
That's easy.
Good. Any questions?
I say that, and you're gonna get the list. They're like
I'm gonna look at the homework.
13 ones long.
Yeah, I get home and they're like, I'm
I'm like, oh, I did this.
Well, then you should probably start it now. There's a handout. Huh?
There's a lot going on in this test.
Squawk.
This test is gonna be